Good morning. Today I will present our machine learning solution developed for ABC Bank to support credit card approval decisions. Currently, applications are reviewed manually by analysts, which can be time-consuming and inconsistent when processing thousands of applications. Our objective was to develop a machine learning model that can predict whether a credit card application should be approved or denied, while ensuring the system remains fair, transparent, and explainable. This is particularly important in financial services because automated decisions must comply with fairness and regulatory requirements. I will walk through the dataset, the modeling workflow, model evaluation results, and how responsible AI techniques were implemented to ensure fairness and transparency. The dataset contains 9,709 historical credit card applications and 20 variables describing applicants. These include demographic and financial features such as gender, employment status, income level, education level, housing status, number of children, and years employed, all important factors when contributing to credit card approval decisions. The target variable indicates whether the application was approved or rejected. We began by exploring the dataset structure. The dataset, as mentioned, contains how many observations and 20 variables that are both numeric and categorical. So we have both types of numerical features. We verified that the dataset contains no missing values as well and no duplicate records, meaning minimal cleaning was required. So as we discovered, there aren't many. So we proceeded. One important observation is that the dataset is highly imbalanced, as can be seen in the histogram. Out of the 9,709 applications, 8,426 were rejected and 1,283 were approved. This means only about 13% of applications were approved. This imbalance can bias models towards predicting rejection, so we addressed it during model training using smooth oversampling. We also examined distributions of numeric features such as income, age, and years employed. These visualizations help identify skewed variables and potential outliers. The correlation heat map shows relationships between numeric features. Most correlations are moderate, meaning multicollinearity is not a major concern for model training. We also analyzed approval rates across demographic groups. For example, students had the approval rate around 33%, working applicants about 13.5%, and pensioners approximately 12%. We also considered gender as a factor, as well as education type, many different factors. We wanted to see how demographic groups were impacted. Then, during pre-processing, we removed the ID column because it's only an identifier and doesn't contain any predictive information and can influence our data. And then we also split the dataset into training and test sets using a 75-25 split with stratification, ensuring the same class distribution across both sets. We implemented a pre-processing pipeline using scikit-learn's column transformer. The pipeline performs the following steps. Numeric variables are imputed using the median, numeric features are scaled when needed, and categorical variables are encoded using one-hot encoding. Using a pipeline ensures that pre-processing occurs consistently during model training and evaluation. To explore model performance efficiently, we first use H2O AutoML. AutoML automatically evaluates multiple machine learning algorithms, including gradient boosting, random forest, deep learning models, and stacked ensembles. The best performing model identified by AutoML was the stacked ensemble model. The stacked ensemble achieved strong performance, including AUC of approximately 0.97 on training data, log loss of about 0.31. These results indicate the model can distinguish between approved and rejected applications very effectively. The confusion matrix shows how predictions compare to actual outcomes. For the AutoML ensemble model, 6,000 applications were correctly predicted as rejected, 802 applications were correctly predicted as approved, and 249 false approvals occurred, and 160 approved applicants were incorrectly rejected. False approvals represent potential financial risk because the bank may approve an applicant who is not creditworthy. In addition to AutoML, we trained several traditional models, including logistic regression, support vector machines, decision trees, and random forest. Among these models, random forest provides the strongest balance between performance and interpretability. The random forest model achieved approximately 95% accuracy on the test dataset, while the auto ensemble achieved slightly higher predictive performance. It is significantly more complex. In financial decision systems, interpretability is critical for regulatory compliance, which makes random forest a strong practical choice. The confusion matrix for the random forest shows that the model correctly identifies the majority of both approved and rejected application. This demonstrates strong predictive performance while maintaining interpretability. We generated a learning curve for our final model, and the learning curve compares training performance and validation performance as the training dataset increases. When the curves converge, it suggests that the model generalizes well to unseen data. In this case, the curves gradually converge as more training data is used, indicating that the model is not severely overfitting. Because credit card approval decisions can significantly affect individuals' financial opportunities, responsible AI principles were incorporated into the model evaluation. We evaluated fairness using gender as a sensitive attribute. Gender is commonly used in fairness evaluation because it represents a protected demographic characteristic in many financial regulations. Evaluating model performance across gender groups helps detect whether the system produces systematically different outcomes for different populations. We measured fairness using metrics including demographic parity difference, equalized odds difference, and selection rate. These metrics evaluate whether approval rates differ significantly between demographic groups. To address potential disparities, we implemented a fairness mitigation method using Fairlearn's threshold optimizer. Logistic regression was used as the base model for this mitigation step because it produces well-calibrated probability outputs that can be adjusted to reduce demographic disparities. This allows the system to balance predictive performance with fairness constraints. To improve transparency, we examined feature importance for the random forest model, and the most influential feature was owned property, indicating that applicants who own property significantly influence approval decisions. Other important features include total income, year, type of working, and the years employed. We also generated partial dependence plots. These plots show how predicted approval probability changes as a single feature changes while other variables remain constant. This helps decision makers understand how variables such as own car or gender influence approval decisions. And as can be seen in our own results, there isn't much influence on the gender, and the gender doesn't necessarily impact the results of our model. SHAP values provide a global explanation of model predictions by measuring the contribution of each feature. We also calculated SHAP interaction features, which shows how pairs of features interact. For example, the combination of income and employment length may influence approval probability differently than each feature alone. The SHAP waterfall plot explains a lot in a single prediction. Blue bars represent the features pushing the prediction towards denial, and orange bars represent features pushing the prediction toward approval. The plot starts with a baseline prediction and shows how each feature increases or decreases the final approval probability. So as we can see, for example, number of the work phone, number phone affects gender, somewhat affects family member size. Different things have different effects. We also use line to explain individual predictions. The orange and blue bars show which features supported approval or denial for a specific applicant. This allows analysts and regulators to understand the reasoning behind each automated decision. From a business perspective, this system provides several advantages: faster credit application processing, reduced operational workload, and more consistent decision making. At the same time, fairness evaluation and explainability methods ensure the model remains transparent, accountable, and aligned with regulatory requirements. In conclusion, a random model, according to a certain metric of AUC, which was deemed most significant in this case, provides strong predictive performance while maintaining interpretability and fairness safeguards, making it suitable for responsible deployment and financial decision systems. Thank you.